So in this video we're going to be talking about section 8.5, which is power series. So a power series is just a special type of series, so all of the work we've done so far will still apply to what we're looking at now, but we've got this special extra thing here where instead of having only n's in here and numbers like we're used to in our series, we're going to allow ourselves to consider a variable x inside of our series. So what does that mean? It's just a variable x like you're used to. You can plug numbers in there and you can look at what happens. So the way that this is going to be set up is you'll have x to a power. It doesn't always have to be n, it could be n minus 1, it could be kind of lots of different things, but just in general we'll have x to the n. Okay, that's what's telling you it's a power series. And then attached to that we'll have this c sub n, which will be more like something we're used to. It'll just be something with n's. So, you know, this could look like a lot of different things. It could look like n over n squared plus 2. It could look like just 1. It could look like n factorial over 4 to the n. Anything you've seen before, any of these sequences we've dealt with inside of series before, that's going to be the piece. So we're just going to write this power series as the x piece and then the regular old n piece that we're used to. And so it's just like a regular old series where we can add up all the terms. So c0 plus then c1 x to the 1, then plus c2 x squared, and so on. Now these c sub n's we're going to call coefficients of the power series. So the actual sequence here that we're used to dealing with, those will be the coefficients because, you know, they just act like numbers, whereas the x is the variable. So we can give you a specific value for x, or, you know, if I have a power series, I can give you an x. You can plug that into the series, and then once you do that, you'll just get a regular old series from the last couple sections. Once you have that, you can tell me, does it converge, does it diverge, what's going to happen? Right? So what I'm doing now is I'm taking this idea of series that we've already dealt with and I'm abstracting it just a little bit to allow myself to vary one of the numbers in here, this x. I'm going to let that vary. I can change it, and then as I change that, my series might converge sometimes, diverge sometimes. We'll see what happens. Right? So this power series, if I look at it at just its terms, what you should see here is it looks like this almost is some kind of infinite polynomial. So it almost kind of looks like an infinite polynomial where the terms are going up, right? I've got a constant term, the c0. I've got a linear term, just a 1 power of x. I've got a quadratic term, the x squared, and so on. So it's almost like I'm dealing with a polynomial, except that I'm just continuing to add higher and higher powers of x to infinity. So you could think of it almost like an infinite polynomial. So given that that's the way I'm thinking about this, I'm going to write this f of x is equal to this like it's a function. Remember, I can plug in an x, and then that would be c0 plus c1 x to the 1, or sorry, 1 to the 1 because that's what x is, c2 1 squared. But what is that really? That would just be equal to c0 plus c1 plus c2 plus dot dot dot. That's a regular old series. That's exactly this series here. And depending on what c to the n is, we've dealt with all these different ways of saying if that converges, diverges. So what we're going to do now is, it's like we're going to ask that question we've just been asking. Does the series converge? Does it diverge? How does this work, right? We're going to be asking that question. But instead of you looking at one specific series like this, you're going to be looking at a power series that if I plug in a number, I get this. I have to check what happens. Then I could plug in a different number and a different number and a different number and keep going. The only problem with that is there's an infinite number of things I could plug into this x. I could do 1, 2, 3, 4, 5. I could do pi, e, whatever decimal I want. So what we're going to need to do is think about a different way to say when it's converging, when it's diverging, that isn't just check every single number and use the tools from the last couple sections. So that's going to be our goal for this for this section is to try to understand these power series, kind of what they look like, how they come up, and then what tools we have for trying to understand when I plug in a specific number for x, is that going to converge or diverge? Because again, every time I plug in a number for x, I get a series out like we're just used to. Okay, so here's our first example. So I'm going to try to think of this as a function. F of x is equal to this power series. Again, I pick a number for x, it goes in there. My question here is, when does this converge? When does it make sense to plug 1 in here and have this series actually mean something? So, when you're getting used to this, you can just plug in numbers and see what happens. F of 1 would be this series, 1 to the n. F of 0.5, so 1/2, would be n equals 0 to infinity of this. And you could just keep trying here. F of 2 would be this series, and so on. And then what we could do is, for each of these series, each of these 3 series, we could ask, does this converge or diverge? And hopefully at this point you're looking at those and going, oh, these are geometric. Each time I plug in an x, I get something geometric. And I know the rule for that. Well, the rule for that is, if my r is less than 1, the absolute value of that is less than 1, I'll converge. If my r, absolute value, is bigger than or equal to 1, I'll diverge. So, how do I use that? Well, my r in this case is just whatever x is, because when I plug in this x into here, it becomes a number to the power n, which we could rearrange to n minus 1, but all that will do is change our a. So hopefully it's not too bad to see that even though this is an n minus 1, it's still going to be the same r. So I take the x, I plug it in for this x in here, and I keep getting these geometric series here. So when is this going to converge? It's going to converge when this r is less than 1, the absolute value, which means that my x has to be trapped in between -1 and 1. And what we did here in this little picture is I've graphed this function here. So the function that I have written here, f of x, is this series, this power series. I typed that into Mathematica, and I put up the Mathematica code for this section, so if you want to check it out, feel free. So I put in this into Mathematica and said, okay, plot from -2 to 2. What you'll see here is there is nothing from -2 up to -1, and nothing from 1 up to 2. We are unsure what is happening here, and unsure what is happening here. Looks like maybe there's an asymptote here. We don't know what's happening at that point. So these endpoints at 1, I mean, we think they diverge based on this analysis we just did with the fact that it's geometric, and we can do that and show that it diverges there. But just pictorially, we're not sure what's happening. So we can use pictures of this to try to get an idea, and it looks like my function is defined here, right? So just to kind of relabel this so you could see it, this is the x, and this is, you could think of as like the y, right? But if you want to, you can think of this as the sum of the series. All right, so for example, if I plug 0 in, this is one I didn't do, so f of 0 is sum n equals 0 to infinity of 0 to the n. Okay, but that's just 0, so what am I doing there? I'm adding up 0 plus 0 plus 0 plus 0, well that's just 0, so that would be right there. And then at each other x value I plug in, I am getting a different sum of that series, and if I can draw the picture, that means that it was converging. Okay, so that fits our idea about this being geometric, is that the picture is only defined between -1 and 1. It looks like that when my r, when this is geometric, is above 0, I get positive sums. When my r is less than 0, I get negative sums. Okay, I'm adding up either positive or negatives. That's hopefully making some sense. So then We can say this converges or diverges. When x is between -1 and 1, this will converge, and everywhere else for x, this will diverge. And how do we know that? Because we know about geometric series. So again, I know it seems like I'm introducing something kind of crazy and new, but it's just going to come back to the fact that I know about series. I know how to say when they converge, diverge. I'm just going to use those tools. So what we just did was a power series centered at 0. Okay, so there's another way to do this. You should think of it almost like, I just did a polynomial, an infinite polynomial, right, where it was centered at 0. So x squared would be an example of a polynomial, not an infinite one, but a polynomial centered at 0. But I don't have to only study this, right? I could study a lot of different things. I could study x minus 1 squared. That would be me shifting it over to 1 here and studying that. It's the same picture, right? It's the same curve, it's just I've moved it over. And so that idea of being able to shift a polynomial that I'm interested in looking at, we can do that with the power series too. I can take a power series and I can shift it or center it about a new number a by just doing exactly what you're used to. So if I want to go and shift this infinite polynomial we're kind of thinking about over to the right 2, I would do x minus 2. Right? So I have this idea of creating a power series that kind of looks like an infinite polynomial at 0 centered, or I can kind of move it all around like I'm used to doing with just regular old polynomials. So you're going to see why we do this in 8.7. I know it's a little weird right now why we would be shifting these random power series things, but you'll get a good sense of that in just a little bit. So there's another piece here that we're going to adopt as a convention, and we're going to say that x minus a to the 0 is 1, even when x is equal to a, for this above definition. So just, this is not really going to come into play, but if you were actually trying to plug in the numbers here, you might write when x is equal to a, you might write that as 0, and we want to think of that as 1. So if it pops up again, I'll mention it, but that's just a little caveat. Okay, so let's get back to an example. Our question here is, when is this going to converge? So when is this going to converge, right? So we're looking at this and we're trying to say, okay, well, I'm looking at it and it's, the problem is it's not geometric. So this piece here screams geometric, but unfortunately, this piece here is not geometric. So it's not geometric, right? So then our ultimate goal is to try to understand, all right, when could this series converge? And it's all about the terms right here. It's all about this, what's happening here. And really what's going to end up happening, just like series, is if there's two pieces, it's going to be all about when these things are trying to battle each other. When is it possible for this to converge? So what we do is we almost treat this x still kind of like a number. Now, we leave it as an x the whole way through, and we make conclusions at the end about it, but you just treat it like it's a regular old series. So if I was trying to understand if this is going to converge or diverge, I see the factorial. I would probably use the ratio test on this. All right, so if I was using the ratio test on something like this, I'd be saying to myself, okay, so when in the world is this going to converge? Well, I need to look at the limit as n goes to infinity of a sub n plus 1, right? And then I divide by, but remember we can keep, change, flip, although in this case it's not a fraction, so we don't need to do that. Easier to just keep it on bottom. Divide by, plug in n. So this is our a sub n right now. Okay, so everything's positive here in terms of the n plus 1. So what I could do if I wanted to is get those out of the absolute value. But I have to be a little bit careful here because remember, x can be any number I want to try to plug in. So these absolute values are going to be important. So what I can do is I can rewrite this as the limit as n goes to infinity of n plus 1 factorial over n factorial, absolute value x to the n plus 1 over x to the n. Okay, and then I got to think, well, I'm doing ratio test. The whole point of ratio test for this is that it's nice and hopefully things will cancel, and they do. So what ends up canceling here? Well, n plus 1 factorial over n factorial leaves me just an n plus 1 on top. Okay, over here, x to the n and x to the n plus 1 leaves me just an x to the 1 on top. So let's keep going here. So then this now is the limit as n goes to infinity of n plus 1 times the absolute value of x. Okay, well, let's think about this. What is this limit, right? So I need to ask the question, how in the world can this limit converge to a number? So I'm looking at this and I'm saying, well, as n gets big, n plus 1 wants to get really big. Okay, so then how do I kind of counterbalance that? I'd have to make x small. But the problem is, no matter how small I make x, n plus 1 will grow bigger than it eventually, and it keeps going to infinity. So this x term is just a constant number, the way we want to think about it. And then this term here wants to grow, grow, grow. So this is not looking good. And the only way that this limit will converge, so this limit will converge to 0 only when x is equal to 0. If x is not equal to 0, then this limit will keep getting bigger and bigger and bigger because this n plus 1. And one way you could think about this is this absolute value of x here has no n's in it, so you could just move it to the outside. It's just a constant the way we're thinking about it. And if x is not 0, this would be infinity. And when you get the limit as infinity in the ratio test, you say it diverges. So if x is not 0, we're going to diverge. If x is 0, our limit's 0, and that's less than 1. So then in this case, we would converge. So this is kind of a boring one, unfortunately. This series is only convergent at one point when x equals 0. So altogether, this series, n factorial x to the n, converges only at x equals 0. So kind of boring. This is a series that converges at one specific x value. So nothing too interesting, but it's one of these cases where you have to see it because it's possible that we have a power series converge at a single point. Most of the time they're not going to do that. They're not going to act that way, but it's worth just showing you that one example. But let's get to an example that's a little more interesting. So in this example, again, now I've graphed this for you. So I show you this graph, and again you see a whole bunch of nothing for some of the x values, and then over here a whole bunch of nothing for some of the x values. And I want you to think about that, see if you can find a pattern in the form of these graphs here. But there are clearly some x values, looks like between 2 and 4, where my function is defined, which means that this series looks like it's going to converge. So here's my guess, based on the picture, that I will converge between 2 and 4. Now, here's the thing. Do I include 2? So do I include 2? Do I include 4? It's hard to tell from the picture, right? It's really hard to tell if there's a dot here and a dot up here or not. So I don't know. I don't know if that's the case. What I have to do is check those individually, those two cases, by just plugging in 2 and 4 and seeing what happens. So we'll do that in a second, but let's do the general case first. So again, I'm going to look at this and I'm going to say, okay, well, you know, the ratio test, I have a combination geometric on top and then non-geometric on bottom. So to me, I'm kind of thinking, well, in that case, let's just use the ratio test again. Okay, so I use the ratio test on this. So this is the limit, n goes to infinity, absolute value of x minus 3 to the n plus 1 over n plus 1 times, we could keep change flip, n over x minus 3 to the n. All right, let's do some cancellation here. We see that there's a little cancellation with the x's. So I cancel this, and I end up with just x minus 3 on the top, one copy of it. Okay, so that's limit as n goes to infinity of x minus 3 times n over n plus 1. But remember, the n's are positive, so I actually don't need them inside the absolute values. So get rid of that. All I need inside the absolute value is the x minus 3. Okay, well, I can take that out because there's no n in there. So now I'm just left with this limit, n over n plus 1, right? And this is a limit we're used to. This is irrational, so this is rational. So I look at highest power on top, highest power on bottom. They have equal power. So I just look at their ratio, and there you go. So my limit here altogether is x minus 3 times 1. All right. Now, ratio test. We got to go back. We're doing the ratio test. What are the conclusions for the ratio test? So this will converge if the limit, this limit I've calculated, which is x minus 3, is less than 1. So it will converge if the limit I just calculated is less than 1. All right, well, hey, that's actually not too bad. Look, I can deal with this inequality. All I have to solve is what x values solve this little inequality here. So this is x minus 3 is less than 1 and bigger than negative 1. Add 3 to both sides, gives me, ta-da! So I know for certain that this power series here, this function I've defined, will be defined, like actually have values, when I plug in any x between 2 and 4, which looks a lot like my picture. Okay, so then you might say, but you haven't still figured out what happens at 2 and 4. So the way we do this is we say this, okay, I don't know what happens at 2 and 4, so let's just check. Let's let x equals 2. I'm going to plug it in. So f of 2, if it exists, is equal to the power series here, but I'm going to plug 2 in. So I plug 2 minus 3 is negative 1 to the n over n. Okay, so then my goal now is to say, what in the world does this thing do? But hopefully this isn't too bad. This is alternating because of the negative 1 to the n. I'll leave to you to show that both of these are true, that it's decreasing, and the limit is 0. So check both these boxes, do the work. It's good practice to check these. But once you see that's true, this converges. All right, so what I get to do from that information is put a little less than sign in here, less than or equal to. 2 is less than or equal to x, because I do know, actually, yes, it is converging there. There is a value there. Okay, so then I just check 4. X equals 4. I plug it in. F of 4, if it exists, would be the sum of this series. So 4 minus 3 is 1. Okay, but uh-oh, I know this one. This is the harmonic series. Harmonic, so diverge. So then this is the set of all values where my function's defined. And there you go. So my function given by this power series is defined from 2, including 2, up to 4. And that's the work. I show kind of the inner points, and then I check these 2 maybe endpoints. All right. So to kind of sum up what we've seen so far, when I give you a power series, there are 3 possibilities. The series converges only at a single point, like we saw at the point 0, and it just so happens it'll be the center of your power series. The series converges for all x. We actually haven't seen an example of that, but we will soon. So it doesn't matter what I plug in, it's going to converge, and it's going to be a function for every x. Or there's a positive number r such that the series converges if x minus a is less than r. We just saw this, right? X minus 3 was less than 1. This was the one that we had just played around with right here. So there's an r, in this case 1, the one we just did, such that it converges, and it diverges, oops, typo, it diverges as long as the x minus a is greater than r, so it's outside of that little interval. So in case number 3, we call r the radius of convergence. Because it's a little interval, we can think of it as having a radius. So it's just that half that length. And then the interval of possible values, the interval of convergence. So in the case we just had, this would be my interval of convergence. And then since half of the distance between 2 and 4 is 1, r equals 1 would be my radius of convergence. All right. So that's the idea of these power series. We have them, we can think of them as functions, almost like these infinite polynomials. But the problem is these infinite polynomials won't always, their values won't always exist. They won't always be defined for every single x I could plug in. A regular polynomial works that way. I could plug in whatever I want. Its domain is all real numbers, but power series, not the same. So I've got a handle on what could happen, so let's just keep trying them. So here's another example. So I've graphed this function again, and again I see nothing in certain places, but hopefully you're starting to see how it looks like I do have some possible interval of values to plug in, maybe -1 to 1. That would be my guess from the picture. So we're going to use the ratio test again. So that's limit n goes to infinity of, and then just to kind of remind you, a sub n would be x to the n over square root n. So this would be x to the n plus 1 over square root n plus 1. Okay, and then it would be times, keep change flip, square root n over x to the n. All right, we're going to do a little cancellation here. Cancel, cancel to just x to the 1. All right, and then my n's are positive, so I can move those out of the absolute value. So don't forget, you can make things as easy as possible on yourself. So this would be root n over root n plus 1. Okay. So then I can move this outside. Limit n goes to infinity of root n over root n plus 1. And I've got my absolute value x. I can just shift it outside. All right, and so now I just need to figure out what this limit is. And remember, there's a handful of ways that we can do this. One way I've seen that people were holding on to is dividing by the highest power top and bottom to kind of try to see what's going to happen here. This is not, unfortunately, this is not a rational function because of the square roots. That's not a good power, like 2, 3, 4, 1, whatever. So we don't have that just looking at higher power top and bottom. Although it does kind of work that way if you think about it that way, just to kind of get an idea. That does work, but we should still try to actually go through and show this. So you have a couple options here. You could try doing L'Hopital's rule if you want on this, but I think the easier way of this is just dividing highest power top and bottom. Okay, so then how do I do that? Well, it looks like the highest power is this n, right? So it looks like I might want to do 1 over n and 1 over n. But the only problem here is if I try doing this, and I try to put this in here so that the n's will cancel, which is the goal. You want these n's to kind of go away. So if I try doing this, then I'm not going to have a great time because I can't just absorb this n in here. So what I could do is make this an n to the 1/2 and an n to the 1/2, and then I could bring it back into the square root. So I'll end up getting square root of n over n divided by square root of n over n plus 1 over n. Okay, these do some nice cancellation. 1, 1. So this would be x limit n goes to infinity of the square root of 1 over the square root of 1 plus 1 over n. Okay, I let n go to infinity. This goes to 0, and that'll give me x times square root of 1 over square root of 1 is 1, so that limit's just 1. And so my answer is that the absolute value of x is less than 1. So then my interval would be 1 to negative 1, and my radius would be 1, which checks out. So then the only thing left to do now is to check the endpoints. When x is equal to 1, that's one of my endpoints, I get the series. Assuming this converges, this would be 1 to infinity, 1 to the n over square root n. Well, 1 to the n is just 1. So then this is f of 1 is n equals 1 to infinity, 1 over root n. This diverges because it's a p series. P equals 1/2 less than 1. So I do not include 1 in this interval. All right. Well, what about x equals negative 1? Plug that in. I'm going to get negative 1 to the n. Oh, don't forget my series. Over square root n. Okay, well, I look at this and I say to myself that, oh, well, this is a alternating. So I could try the alternating series test. Okay, so then I just have to check, is it decreasing? So again, either do the algebra or take the derivative of 1 over square root x and show that that's negative. And then I have to just show the limit goes to 0, and this isn't too bad. So this isn't too bad. You know, this one's actually not too bad either. For this one here, remember, you can just, if you want to do it algebraically, it would be 1 over root n plus 1 needs to be less than or equal to this. Cross multiply. Right? And then you could say a couple things here. You know the square root function is increasing, so if I plug in a bigger thing, I'm obviously going to get bigger. Because everything is positive here, you can square both sides, and then you get 0 is less than or equal to 1. That's true. So a couple different ways you could attack that, but you end up getting that this converges by the alternating series test, and so we would say include that. And there you go. So hopefully not too bad. Okay. Let's try another one. So here's another picture I have of this. It looks like we've got a longer interval here. Looks like maybe it goes from -4 to 2. Although I could have just not included some of the domain to the left. So it could go even further. So let's check. Let's look at it. So I'm going to do the ratio test. Limit n goes to infinity of, so I'm going to get n plus 1 x plus 1 to the n plus 1 over 4 to the n plus 1 times, so keep change, flip this, 4 to the n over n times x plus 1 to the n. Okay, let's do some cancellation if we can find it. Cancel, cancel, that'll leave a 4 down here. Cancel, cancel, that'll leave an x plus 1 up here. Alright, this is limit n goes to infinity of absolute value of x plus 1 over 4. And then what else do I have left? So that was those two. I've still got my n plus 1 over n. Okay, now the n plus 1 over n, I could just take that out if I want to. So let's move that out of the absolute value. Okay, and then this x plus 1 over 4, well, you know, I don't actually need that inside the limit because there's no n. So let's move that out. Okay, right, so This limit, again, you can do the same idea here. It's the highest power on top divided by the highest power on bottom. So this limit's 1. So this is 1. And so altogether, we end up with this total limit being x plus 1 over 4 times 1, which is just that. And then our question is, when is this less than 1? So to converge, I need it to be less than 1. So I've got a job to do. How do I do this? I've got to kind of pack or unpack the x. I've got to get to the x. So I'm going to move the 4. So at first, actually, I'm going to get rid of the absolute value. I should start there. So I'm going to get rid of the absolute value. So that's x plus 1 over 4. I guess it doesn't really matter. Then I'm going to multiply 4 on both sides. I'm going to subtract my 1. And there we go. So I'm off by a little bit here in my picture. It looks like this goes from -5 up to 3. So that's my interval at this point, okay? And so then the radius here would end up being 4, because that's the distance between -5 and 3, but I only want half of that because it's a radius. Okay, so then what do we have to do? We have to check the points. So let's check x is equal to -5. So I'm going to plug that in, and I'm going to get f of -5, assuming it exists, is this. So I'm going to get n times, okay, what happens here is I plug -5 in, I get -4 to the n over 4 to the n. Well, that's equal to n times, so -4 over 4 is just -1. So this would be n times -1 to the n. Okay, so we can do the limit as n goes to infinity of this sequence here. And this does not exist. This limit does not exist because as n gets really, really big, so will this n, because it's just n gets big. The -1 will just bounce me up and down, up and down, up and down. So since this limit of the terms does not exist, by the test for divergence, this diverges. So we are not going to include this. So let's try the next one. So this would be x equals 3. Okay, I plug that in. I'm going to get n equals 1 to infinity, n, and then 4 to the n over 4 to the n. Well, those cancel. I get n equals 1 to infinity of n. Well, that's definitely diverging. Same idea. The limit as n goes to infinity of n is infinity. So then this diverges. So I don't keep either of those. Boom, boom. All right, so as we saw, that's the end of the slides. So I know that there's a lot to these examples, and we're bringing in a lot of stuff, right? So we're using the ratio test on these, but then we have to check the endpoints, which means we could get a new series that's back toward any of our other series we had tried. We used the test for divergence, alternating series test, p-series, all of those came into this problem. So there's a lot to this, but just take it one step at a time and make sure you ask questions.